Thanks, David. Yeah, so this was my first slide, and David, you should borrow this slide, right? So the holy grail of pseudorandomness, well, you probably saw this talk already. What I'm going to talk about is the other holy grail of pseudorandomness. So what is this? Well, let's say it's a pseudorandom generator that takes a random seed of length log n and stretches it into n bits that look truly random to any small circuit, say a circuit of size n squared. Okay? So this, of course, would imply that P equals BPP, and randomness doesn't add much power to computation in the big picture. Why would we believe that such, magical objects should exist? Well, this long and beautiful line of work tells us, starting with the observation of Yau, then Nissan-Wigderson, Impagliazzo-Wigderson, it tells us that if sufficiently strong lower bounds hold, we think they should, then in fact such pseudorandom generators exist, right? Extremely strong pseudorandom generators. But on the other hand, proving that a PRG actually fools a class of functions, it's a pretty strong, it's a pretty strong diss to that class. It gives very explicit lower bounds for that class of functions. So this also tells us that we are unlikely to find this holy grail anytime soon. Okay. Given the state of affairs, what could we hope to do? What is the hope for unconditional construction of pseudorandom generators? Well, certainly when you have a specific algorithm in mind, you could hope to mitigate or completely eliminate the use of randomness for that particular algorithm. This doesn't require any lower bounds. This is a program which has had some spectacular successes, like primes is in P and the ST connectivity algorithm. In other settings, like hash functions and streaming algorithms, getting short random strings is actually crucial for algorithmic efficiency, because usually in hash functions or streaming algorithms, you're thinking of some input which is like the number of documents on the World Wide Web or something like that. You really don't want to store an explicit random function on this large an input, right? So here pseudorandomness is essential to, say, the space complexity of these functions. This is something which is going to be very relevant to this talk today. The other thing you could hope to do is to actually construct explicit PRGs for those classes of functions where we do know explicit lower bounds, right? Because here, if you have lower bounds, sure, you could hope to actually construct unconditional PRGs. This is a program which has met with considerable success in the case of bounded depth circuits, starting with the work of Itai-Wigderson, and space-bounded algorithms, right? So bounded depth circuits, we have lower bounds against these, and for space-bounded algorithms, the right model of computation happens to be read once, where you just stream over the random bits. So again, lower bounds are not really an issue with this model. Okay. So now we could ask, at least for these classes where we do have lower bounds, do we now know how to construct optimal pseudorandom generators which have seed length log n? And you probably all know that the answer is not really, not quite yet. For space-bounded algorithms, log space algorithms, there's a long and beautiful line of work, this breakthrough result of Nissan from the 90s, which gave seed length log squared n. Now, I don't want to give the impression that all these papers after that did nothing much. They're all very nice papers. Many of the authors are in the audience, so I won't say that. But the best seed length is still log squared n, right? What about AC0 circuits? Well, let's just focus even on DNFs, which are depth 2 circuits. Here, again, the best PRGs we have. You'd think that these are DNFs. There's presumably nothing interesting new to prove about them, but that's not the case. Again, the best pseudorandom generators we have for them have seed length log squared n. Okay? And now you could ask, well, are these the important open problems or the important closed problems in pseudorandomness? How important is it to get this log squared n down to a log n, right? Well, many of you are here for a semester-long program on fine-grained complexity measures. So presumably you already believe that getting the exact polynomial is important. But some others, if you're just here for a week, let me try and justify it to you why we should actually care about this. Well, if you manage to get the seed length down to log n for bounded space algorithms, this is one way you could hope to prove that RL equals L, that randomness doesn't drastically reduce the memory requirement of an algorithm, which is an important goal of computational complexity. Similarly, we do have lower bounds for AC0, but we could have better lower bounds than the ones we do currently. And in fact, this seemingly innocuous problem of constructing a better PRG for DNFs, in fact, even if you get a hitting set generator which beats this log squared n, it would lead to a better lower bound against depth 3 AC0, right? Okay, so what is today's talk about? Well, I'm not going to solve either of these problems, but I'm going to show you a technique called the gradually increasing independence paradigm. What it is an iterative technique for constructing and analyzing pseudorandom generators. It more or less came up independently in these two works by Kane, Mecca, and Nelson on de-randomizing the Johnson-Linden-Strauss lemma, and Sellis, Reingold, Wieder, and Segev on hash functions for load balancing. And by now, so this is a long laundry list of things. What it does is give us optimal constructions of pseudorandom generators for a large class of simple functions, which we needed to fool first in order to make any progress on these two questions, either fooling RL or fooling AC0 circuits. So we're going to see some of these in greater detail, so just some highlights. I mentioned Johnson-Linden-Strauss and load balancing. It fools things like combinatorial rectangles. It gives you optimal families of min-wise hash functions, gives you a PRG for half spaces, and so on and so forth. Now, when I say optimal seed length, it leads to seed length which is logarithmic in all the relevant parameters, which is the input length n and the error epsilon that you're trying to achieve. When I do this, I'm hiding some log n factors, and I'm going to do this throughout the talk. If you care about this, then go talk to Raghu after this talk. So why is this an interesting thing? Well, it turns out that, prior to this, there weren't really a whole lot of natural classes of functions where we could really get the right seed length in terms of both n and the error parameter epsilon. Like, the really important example we knew was epsilon bias sets. These we've known how to construct for more than 20 years now. But in a lot of other things, one of two things would happen. Either the dependence on n would be some larger polynomial, or else when you try to get the error, which is inverse polynomial in n, then your dependence on epsilon is not too great, right? Okay, so what I'm going to do in this talk is just show you the development of this idea in three, hopefully 3 steps of gradually increasing difficulty. So first, we'll talk about hash functions for load balancing. This is this work by Sellis, Reingold, Segev, and Wieder. Then I'll show you how to construct PRGs for combinatorial rectangles. And finally, if time permits, we'll talk about PRGs for half spaces. All right? Okay. So let's start off with the load balancing problem. So this is, one of the very first things that you encounter in any course on randomized algorithms. Say you throw n balls randomly into n bins, then with high probability, no bin is going to get more than log n balls. It's actually log n over log n, but let's ignore that. Okay? So you can think of this as a hash function where you took your jobs and assigned them to machines or something like that, except now you needed n log n random bits to select a truly random bin for each ball, right? Is there a small family of hash functions specified by ideally log n bits of randomness, which will give you the same kind of guarantees that no bin is loaded too heavily? Okay, so one observation is, well, you can do this by using considerably fewer random bits, by using log squared random bits. How do you do that? Well, it's not easy, it's not hard to show. It's very easy to show that log n-wise independence suffices for this, right? And intuitively, you're only worried about events that involve log n balls. Why would you need more, right? We'll see this in more detail, but log n-wise independence suffices. And since generating a k-wise independent random string of length n requires seed like k log n, this immediately would tell you that seed length log squared n is sufficient for ensuring this max load property, right? And perhaps surprisingly, there was nothing better known even for this very simple load balancing problem until this work, which I'm now going to talk about, which gives you seed length log n. Okay. So before I tell you this, how this result goes, let's go back to this, this classical, let's revisit this fact that log n-wise independence suffices, all right? So we're throwing balls into n bins. We have n balls in n bins. Let's just look at this experiment from the perspective of one bin, right? So what's happening here is that there are n balls. Each of them is going to land in this bin with probability 1 over n, right? So, the number of bins in this, the number of balls that land in this bin, this is a Poisson random variable with mean and variance 1. So this is a distribution we know everything about, right? So the statement we want to de-randomize is something like this, that the probability that the load will actually exceed log n, we would like to show that it's polynomially small in n, because if we manage to do that, we'll just do a union bound across the various bins, okay? Now, there are many ways you could try and prove this with limited independence. More or less, it'll amount to some kind of higher moment computation, right? So if you look at this distribution, it has mean 1, it has variance something close to 1. So the probability of seeing a deviation like log n, well, if you use Chebyshev, it'll tell you like it's something like 1 over log n squared, right? Which is a fine bound, but it's not strong enough to use a union bound now across n bins. You could use higher independence. You could use k-wise independence. For k some constant, you'll get 1 over log n to the k. It's only when you use k, which is something like log n, that you get the polynomially small error that you need in order to take a union bound. So that is why this doesn't give you anything better than log n-wise independence. Okay. So now, the genius of this result was to say, well, we want to throw n balls into n bins. Let's not do that quite yet. Let's first throw n balls into root n bins and see what happens, right? That's work enough already for us. Okay, what happens now? Let's again look at it from the perspective of just one bin. There's n balls coming in. Each of them is going to land here with probability 1 over root n. And now something very important happens, which is that the number of balls that's going to land in this bin, it's now distributed like a Gaussian, okay? Which has mean root n. And in Gaussians, it's always, it's standard to talk about mean and variance. Here, the variance is also root n, but what is important is the standard deviation. That's only n to the 1/4, which is, this is the regime we are all familiar with. The standard deviation is much smaller than the mean. So what this means is that even to see a load of 2 times root n, this is a very unlikely event, right? Moreover, what is important for us is that this is very easy to de-randomize, because already if you just use Chebyshev's inequality, it'll say that the probability of this event is going to be something like 1 over root n. So this is not strong enough yet to use a union bound, but you can fix that by using k-wise independence for some constant k, like say k equals 10. If you use k-wise independence, the probability you'll see max load, which is much larger than say 1.1 times root n, is going to be really small. It's like n to the minus k, okay? So here, something really nice is happening, which is this. In order to generate a k-wise independent random string of length n, it requires seed length, which is like k log n. And you get this k log n back in the error exponent, right? Whatever you invest in the seed, you're able to drive the error down just by something exponential in that. And this is a property which is going to be used time and again in our constructions. Okay, we're not done yet. We've just thrown n balls into root n bins. But now we can iterate, right? We take each of these, the first step on day 1, we take the n balls, we throw them into root n bins using something like 10-wise independence. Now on day 2, we come back, we look at each of these root n bins, and they have something like perhaps at worst slightly more than root n balls. For each of these bins, we throw them into n to the 1/4 bins now. We're just iterating. We use different bins, for these root n things, but we're going to do 2 things. Firstly, since we've gone from n to root n now, we can afford to double the amount of independence that we use. Because the seed length for k-wise independence, remember, is k times log n. If this n becomes root n, you've saved a factor of 2. You can use that to increase the amount of independence. So we can double the amount of independence we're using within a bin. Of course, we have root n bins now to take care of, but we're just going to do a union bound across these bins. So we can just use the same randomness across bins. Okay? So you keep doing this, and in log n steps, you'll get done, and you'll get the right kind of load. Right? So what's going on here? In each step, you use order log n random bits, and you get a polynomially small error bound. And this allows you to just, there's only log n steps here. So at the end of the day, you've done the right thing, and you have inverse polynomial error bounds. Okay? So from this, I want to come up with some kind of template that we're going to use for constructing pseudorandom generators now for more complicated tests even. Yes?
Do we know that
No.
k-wise independence, it would not work?
No, but I think you could prove this.
You could come with a counterexample.
These things are, I would ask Raghu to do it, but I think it can be done. I mean, these things are pretty well characterized in terms of the polynomial, the norms of the polynomials and so on, and I think here you're trying to fool a polynomial of large norm. Yeah. But, these things they're often notoriously tricky to prove. Like, I think even just epsilon bias, does it fool half spaces? I don't think we really know it doesn't. Or the XOR of 2 epsilon bias fools log space. So these things, yeah, they're tricky. Okay, here's the template that I want to, this is the template we're going to use. It is that if an event is predictable, right, it shouldn't require much randomness. When we were throwing these n balls into n bins and we were looking at just one bin, then there was some real uncertainty there. Am I going to get 0 balls? Am I going to get log n balls? Any of these things could happen, right? On the other hand, when you're throwing n balls into root n bins, you know that every bin is just going to have root n balls, and there's some standard deviation, but it's a lower order term, right? So events like these, they ought to be easier to de-randomize. So the template that we're going to come up with is take some event which is interesting and break it into a series of predictable events and hope that each of these events is easier to de-randomize by increasing the amount of independence that you use in each stage. Emanuele?
I didn't understand the difference that you were making between,
the Poisson and this thing, the Gaussian. Yeah, that's, I'm not trying to be formal here.
Root beans.
I'm sorry?
The throwing into m beans versus root n beans. In what sense is one more?
Yeah, because in one sense, you were dealing with the Poisson distribution, right? Where, you're in the setting where mean and variance are roughly about the same. They're both constants. And, it's, limited independence is particularly good at getting things like moment bounds, right? So in the first, I'm not trying to be very formal here, but in the second setting, right, you were in the scenario we are very familiar with, where you have a deviation which is much smaller. The standard deviation is much smaller than the mean. So proving a sharp concentration result in that setting was very simple. So I'll try and make this slightly more formal as we go along, but it's not going to be a whole lot more formal. Okay, so I'm now going to try, so this is our template. We believe that somehow events which are, more predictable, where there's not a whole lot happening, they should be easier to de-randomize. So we'll take an event and try and break it into a series of predictable events.
Yeah. Version is basically what you're saying. If an event is predictable, then basically you invest t bits of randomness, you get 2 to the minus t error.
Right.
And if an event is unpredictable, then you're wasting.
Well, okay, so yeah, I'm not trying to make that formal a statement quite yet. This is just intuition. But that's the general idea that, Okay, let's see how this could work in the setting of combinatorial rectangles. So what are those? We've talked about throwing balls into bins. Now we're going to talk about taking balls out of bins. Okay? So here's the setting. you have n bins. Each of them has some number m of balls. And you can think of n and m as being the same, if you like. Each of these balls have two colors, black and white. So what we do is we reach into each bin and we draw a ball out at random. And now the event that we're interested in is that all the balls are black, let's say. So what is the probability of this event? Well, if the first bin has a pi fraction of black balls and the second bin has a p2 fraction, it's just the product, right? So what we'd like to do is come up with a pseudorandom strategy for drawing balls from bins, which maintains the probabilities of events like this one. So let's be absolutely precise here. A draw of a ball from a bin, you can think of that just as a hash function from bins, which are numbered 1 through n, through balls in that bin, which are numbered 1 through m, right? So when you draw each ball uniformly from each bin, you draw balls uniformly from every bin, then you get all the balls being black with probability, which is the product of the PIs. But of course, this requires n log m random bits. We want a hash family, which ideally uses logarithmic number of random bits for this. So these kinds of events, they go by the name of combinatorial rectangles. Yeah, it's a long line of work in pseudorandomness. The nice thing about this problem was that it was on the critical path, both for doing something better for AC0 and for RL. Okay? So there's been a considerable amount of interest in it. And the best construction known before our work was due to Lu, which gets a seed length of log n, which is great. But the dependence in 1 over epsilon was something like log 1 over epsilon raised to 1.5. So in the inverse polynomial error range, it was not quite log n, right? And this is an extremely natural class of tests that you could, this is a very natural class of tests. You'd imagine that it shows up in many different settings. One that I'd like to mention is this observation, this nice observation of Sachs, Srinivasan, Zhu, and Zuckerman, saying that if you want to construct min-wise independent hash functions, you'll get them from a PRG for combinatorial rectangles, provided you can do, this reduction works in the range where the error parameter is inverse polynomially small. Okay. So we're going to try and apply our template of doing things gradually to this problem. So here's what we're going to do. We want to draw one ball from each bin. Well, on day one, we come and we eliminate most of the balls. We keep root m balls from among the m balls in each bin. And we say, OK, that was already a lot of work. We're done for the day. On day two, we come back and we reduce root m down to m to the 1/4. And we're done. Okay? We go on doing this. And log m days later, we finally have selected one ball from each bin. Okay? Now, of course, this is just a gloriously lazy way of doing the same process of choosing a random ball from a bin. But the hope is that now you don't need to use true randomness, that there's so little happening in each stage that you could get away with using limited randomness. Of course, you'll need to increase the amount of randomness as time goes by. Okay. So does this actually work? So let's have a look. So what happens? So let's just analyze what happens on a single day, right? If we can prove that limited randomness does the right thing here, then we're more or less done. So on day one, what am I doing? I had m balls in each bin. Now I'm just keeping root m balls from among these m balls, and I want to do this using some kind of limited independence. So what is it exactly we would like to achieve through this process? Well, I'm sampling these balls from each bin. So the fraction of black balls in a bin that's remaining after day one, it's now a random variable. And these random variables are correlated across bins. But if I can ensure that this product of these random variables across bins, in expectation, it does the right thing. The expectation of this product is what it should be. It's the product of the PIs. Then you can imagine that we are doing OK. Then if we actually did our rest of our decisions uniformly at random, we'd be doing the right thing. And maybe we can try and de-randomize that as well. Okay? So this is our goal. We want that QI, which is the fraction of black balls left in each bin, this is going to be a random variable. There are going to be correlations, of course, but we'd like the product of the QIs to have the right value. Yeah.
Are you assuming that the product of the PIs is relatively large?
Yeah, so you only care about a pseudorandom generator with error delta. So, if this product of the PIs becomes too small, then yeah, you can assume that it's at least delta, which is the error you're shooting for. Okay. So here's the good news. Assume you're just sampling these balls from within each bucket using just pairwise independence. Then, of course, the expectation will be correct. This is like just taking an opinion poll, right? And the variance will also be small. It reduces, we know that the error in your sampling reduces with the number of samples that you take. So the variance is going to be something like m to the minus 1 over square root m. That's the good news. But now we want to use limited independence across the buckets to multiply these QIs, right? And this is the part which really sounds like crazy talk, because we know that k-wise independence, it's fine when you care about polynomials of degree k in your random variables. But here what we're trying to fool is a polynomial of degree n, right? It almost sounds that, it almost seems like this shouldn't work, because if you can fool the product of everything, this seems like the thing that should be hardest. So then, you should be able to fool anything and everything. So the thing that's going to work in our favor is the fact that these are actually probabilities, and they're bounded in the range 0 to 1. Okay? So here's the question that we're trying to answer. If I have a product of bounded random variables, is it then true that bounded independence suffices to approximate the expectation of the product? You want it to be the product of the expectations. So here's the setup. I have random variables x1 through xn. Each of them are bounded in the interval 0, 1. Now, if they were truly independent, then I know that the expectation of the product equals product of the expectations. I would like something like this to be true under limited independence. So this is a question which was already addressed in this work of Even et al., which they proved that you can get an error bound of 2 to the minus k if you use k-wise independence. This is already surprising to me, but in fact, for what we want, it's not going to be good enough. Because remember, we kind of want the seed length back in the error exponent. So we really want an error, we want error like n to the minus k out here. Okay? Okay, so, the first thing we do is to change we look at a more general problem. Let's say the random variables are in the range minus 1, 1. What can you say about such things? Of course, you're not going to get a stronger bond because this is a more general thing. But something more interesting happens, which is that even this theorem goes away. And there's a very trivial counterexample. It's just parity. Suppose x1 through xn minus 1 are uniformly random bits, and then I just take xn to be the product of x1 through xn minus 1. Right? Now, this distribution is n minus 1 independent. But if you compute the expectation under the uniform distribution, that is 0, whereas if you take the product of all these things under this distribution, it's going to be constantly 1, right? So you cannot have a statement like what they prove in this more general setting. But the good thing is that this kind of tells you what you need to assume in addition to have such a bound. It turns out what you need is a bound on the total variance, right? So the statement which I'm going to tell you, it's in this work with Amir Yehdayev, and it's kind of a real clarification of something we were doing in the earlier paper. We say that if you have random variables x1 through xn, which lie in the range minus 1, 1, and assume you have k-wise independence, you can bound this error by the sum of the individual variances, the total variance, raised to the power k. Okay? Now, each of these are random variables in the range minus 1, 1. Their variance is a number between 0 and 1. The sum of variances is some number between 0 and n. Okay? And I've given you a statement which is only meaningful when the variance lies between 0 and 1. In particular, if the variance lies between 0 and half, then we are actually getting an improvement over this bound. Right? So this seems like something which is extremely specific. Why is it of any use? Well, let's go back to this setting here. It turns out just by this pairwise independence sampling, you can ensure something much stronger than the variance of each QI is small. you can ensure that the variance of the sum is roughly something like 1 over m to the 0.1. I'm not going to tell you why this is the case. You just do the calculation carefully, and then you'll see that this is actually true. Okay? So now we can apply this lemma, which I showed you pretty immediately. If you're using k-wise independence across buckets, then the expectation of the product, it's roughly what it should be, with an error term, which is m to the minus 0.1k. So this thing of wanting the seed back in the exponent, you actually get that, right? So what you can do now is keep on iterating it. As you go further and further, this number m goes on dropping. So you can increase the amount of independence while ensuring that the error stays really small, inverse polynomially small at each stage. And log m days later, you use seed length, which is something like log n times log m, and you're done. Okay. So any questions about this? Yeah, Emmanuel?
Pairwise independence in each bucket. So I don't understand. Can you tell us how the calculation is done? So
I'll show you this later. So yeah, it requires some.
I mean, if you just.
Okay, so basically what's going to happen is the variance in each bucket, right? So what is the random variable you're looking at? You took independent samples, you averaged them out, right? What is the average bias of this bucket? That's the random variable you're looking at. The variance will really look something like pi times 1 minus pi over m, over root m or something like that. So it's not just 1 over root m, you have this pi times 1 minus pi factor. That's why when you sum it, you actually get something. It's related to this thing Russell said, that in the interesting case, you can assume the sum of the pi's is not too large. If you want to see it, we can do this calculation later. Okay? All right. So going back to this template, right? So what this tells us is that we can try maybe, here's one attempt at formalizing what predictable ought to mean. If you have a sequence of variables where the total variance is not too large, then maybe there you can get away with limited independence. Okay? So now we're going to use this template and apply it to constructing PRGs for half spaces. Though in fact, I'm going to talk about not half spaces, but a more general class of functions which you've probably not heard of before because we just defined them in this paper which hasn't appeared yet. They're called, so we call them Fourier shapes. So what are Fourier shapes? It's again the setting where you're drawing balls from bins, but now the balls have colors, right? They're allowed to have infinitely many colors, and in fact, these colors are going to be coming from the unit complex disk. So each ball has a color. The color is a complex number of norm at most 1. Right? So, okay, so each ball has a certain color. Now what do? You draw these balls from the bins. Okay, so you have a complex number for each of these balls, and then you multiply them together, right? Since multiplication in the complex plane is essentially rotation, you can think of this as mixing all the colors together. And then you finally get a color which is obtained by taking this product. It's also going to be a number in the unit complex disk. Okay? And now what do I want to do? Like before, I want a small family of hash functions that fools this collection of somewhat esoteric functions, but only in expectation. Okay? So let me just tell you why this is something non-trivial. So this color is finally going to be some random variable distributed on the unit complex disk. Let's say it's uniform on plus and minus 1. Its expectation is some other complex number. And all I want is that when I draw these balls pseudo-randomly, the expectation I get is close to this expectation. I'm not asking to get the distribution right. And this is an important difference because, for instance, there are so many ways of getting expectation 0 in this, and they're all the same as far as this definition goes. Okay. So we started off by saying we wanted max load in every bin to be small. Then we said we wanted to fool the probability of some event. Now we're fooling the expectation of some complex valued random variable. Why would you care to do that? Okay. It turns out that this can encode a lot of things which they're pretty much in RL. These are classes of natural functions that you need to fool in order to get a pseudo-random generator for randomized log space. One example is modular tests. So these are things where you get to sum up subsets of bits, but then you take it mod some modulus, and this could be a pretty large modulus of size like root n. Right? So this is a generalization of parity and so on. In the large modulus case, we didn't know how to fool these things with small seed lengths. Half spaces is another example which can be, half spaces are just linear classifiers. This is another example of a class of functions which, it's received a lot of attention, and it turns out these Fourier shapes capture half spaces. Combinatorial shapes, what are these? Let's go back to the case where there's only 2 colors of balls in each bin. Now I draw balls from every bin, and then I have some function on the number of black balls. I could say I want it to be even, I want it to be at least 10 or something like that. So it's a fairly natural class of functions. So it turns out that fooling Fourier shapes suffices to fool all these classes of functions. Yeah, Russell?
Have you told us what a Fourier shape is yet?
Oh yes, it's this thing right here. You have a coordinate function, each of which it maps 1 through m to a unit complex number. It's the color within each bin, and then I just take the product across bins.
Okay, I didn't understand.
Sorry, yeah, these are Fourier shapes. Yeah.
And the UIs are just the individual bin expectations?
The individual expectations, yeah. Exactly. Oh, sorry, yeah. Lots of notation showing up sneakily. Yeah. So I have these coordinate functions for each coordinate. And then what I do is, if I pick randomly, I get some kind of distribution here. I look at the expectation of that. Now I want to be able to draw pseudo-randomly such that when I take the product, I have roughly the same expectation. So let me just tell you one thing about where this connection comes from. It comes from the discrete Fourier transform, right? Let's say you're thinking about half spaces. What this essentially means is that you have some weighted sum of 0, 1 random variables. They are weighted by some integers. You're looking at their sum. You want to understand the distribution of this random variable. Now it's an integer random variable, and its Fourier transform at some value theta is going to be given by the exponential of I theta times the random variable. You do this usual trick of you have a sum in the exponent, you turn it into a product. And what you'll get here is a Fourier shape. Okay? So I'm not going to tell you more about this, but basically we are kind of trying to fool functions by looking at their Fourier transform. That's what's going on here. All right. So what we give is a generator for Fourier shapes, which has seed length, which is logarithmic in all the relevant parameters, which is the alphabet m, the dimension n, and this error parameter 1 over epsilon. We are hiding some log squared terms here. Okay? And maybe in the next 4 minutes, I'm just going to give you a very high-level idea of how the generator for this thing works and how it generalizes what we've seen already. Okay. The first thing to observe is that high variance. So, it's going to be all about the variance. And the first observation is that high variance lowers expectations. What do I mean by this? Let's say we have a random variable in the unit circle, and it has high variance, which means it's all over the circle, right? So you'd imagine that this naturally pulls the center of mass. So the expectation is just the center of mass of these points, and you'd imagine this pulls the center of mass towards the center. So if the variance is very high, then the expectation is small in magnitude. And you can actually prove that. It's a simple calculation. Okay. So this tells us something about the expectation of any Fourier shape like this. Under the uniform distribution, you'd actually be taking the product of the individual expectations. Now, every time one of these fj's has high variance, its expectation is going to be small. So the overall expectation goes down a little bit. So if the total variance is high, the expectation of the Fourier shape is going to be small in magnitude, right? So this is useful because all we want to do is to fool these things in expectation. So all we need to ensure is that our PRG also gives us an expectation which is close to 0, right? So I won't say a whole lot about how this is done. The kind of Fourier shape you should have in mind for this is just parity functions. Naturally, the PRG is some extension of the Nauer and Nauer construction of epsilon bias sets. You need to choose the right construction, the one where they do gradual amplification. They basically build it with their bare hands. It turns out that you can lift that construction to this more general setting. The interesting case is where the variance is small. Okay? And I'm just going to focus on the case where the alphabet within each bin is of size 2. This corresponds to the case where the inputs are bits. Depending on the input, you get either this or that complex number from each bin. All right. So the first thing we're going to do, simply because it's worked for us in every example we've seen so far, is to just hash these n coordinates into root n bins, which contain roughly the right number of coordinates in each bin. So let's say we hash them into root n bins. Each of them contains root n coordinates. What do we do within each bin? Let's say we know how to solve the root n dimensional problem. We have a very good PRG for it. We're going to use that within each bin, right? Now the real tricky question is, what are we going to do across bins? Because there are root n of them. So if you use independent seeds, then your overall seed is going to be root n times log n, and you don't want to do that. Okay. So now the key idea is you can think of a pseudorandom generator for the root n dimensional case as a gadget which takes a Fourier shape over an alphabet 2 and dimension root n and converts it into one single shape but over a much larger alphabet, right? Because what is a PRG for these things after all? If you actually pick one item from each of these bins, you're going to get some distribution on 2 to the root n complex numbers. The PRG is just replacing this with a smaller collection of size poly n, perhaps, such that the expectation is roughly the same. So if all you care about is expectations, you can take this root n dimensional object, replace it by one Fourier shape, but it needs to be over a much larger alphabet now. The alphabet size will be 2 to the seed length. Okay? All right. So with this view, we can think that we've taken these n Fourier shapes, and we've reduced it to the problem of fooling root n of them, but over a much larger alphabet, right? And now we want to know, how do we recycle seeds for these things? But this is why it's nice to work with a larger alphabet, because what you have now is just one Fourier shape in root n dimensions, but over a much larger alphabet. So instead of choosing independent seeds for each of these things, you can recycle the seeds using a pseudorandom generators now for a larger alphabet in root n dimensions. Okay? So in essence, what you're trying to do when you have independent seeds is just to fool this Fourier shape, which is in root n dimensions and over a large alphabet. So you can just recycle these seeds using a PRG. So in essence, what we've done is to reduce the problem of constructing PRGs for an alphabet of 2 in n dimensions to an alphabet which is huge. Think of this as n to the 1,000, but in root n dimensions. So is this really progress? Well, perhaps not yet, but we can reduce this alphabet using this kind of repeated sampling that we used in the case of combinatorial rectangles. So in the first stage, we'll sample square root m from each bucket. 2 to the r will become 2 to the r over 2. You go on doing this, and in log m steps, you'll actually have made progress. You'll have reduced 2, n to 2, root n. Okay? So this is, of course, a very fast and furious description. It's not even clear from this why low variance should have anything to do with anything at all. And it turns out the main technical lemma that you'll use time and again in proving that this actually works, and it does actually work, is this generalization of this lemma we had earlier to numbers which are bounded in the unit complex disk. That if you take the product of variables which have low variance, then k-wise independence is sufficient to fool them in expectation. All right, so let me just summarize by saying that, so this technique, it's a pretty, in retrospect, a fairly simple and natural technique, even if proving it takes some effort sometimes. And it seems to do a lot of things that we knew we needed to do in order to make progress on these problems, like constructing better PRGs for RL. Now, I hope that this will actually be applicable to more things, but it's, so here is where we're stuck at as far as RL goes. We can fool a lot of functions, but they all have this property. Like take a half space. These are not exactly in log space, but they're well approximated by log space things. And this holds irrespective of the order in which you see the bits. The same for things like mod tests and so on and so forth. Everything that we fool, we seem to be only able to fool functions which are going to be in log space no matter what order you see the bits in, right? And it's a real challenge to see whether you can do anything for things which are only in log space when the bits arrive in the right order. Now for AC0, we are able to fool read once CNFs and DNFs, because read once, it naturally means that in computing the expectation, there's some product going on, and you can imagine that all the technology we have is very useful for that. Could this do anything beyond the read once case? If it could, can it fool all CNFs, for instance? That would be really nice. And finally, just the fact that in order to compute the expectation of the product, you don't need full independence. I think this is a somewhat surprising fact. A lot of times in the analysis of algorithms, why using independence is because you have some expectation of products and you want to be able to compute it. So maybe the fact that there's a natural setting where you can get away with limited independence, hopefully it could find other algorithmic applications. All right, so I'll stop right here. Thanks.